Okay, so like we mentioned, the first thing you guys need to know when you're doing this section is if you haven't already memorized the strong acids and bases, you're a little behind. So if you don't know them, write them down and memorize them. Okay? Here's the 6 strong acids. And for strong bases, it's pretty simple if you have a periodic table. The first row, alkaline metals, those cations are all strong bases. Okay? So KOH, NOH, the first column, all strong bases. Second column, calcium and down are strong bases. So magnesium and beryllium are not strong bases. Okay? So first column and second column, calcium and down. It's fairly simple. So, like we mentioned, we feel like people were doing pretty well with acids and bases until we got to this last lecture. And there's been like a ton of questions about salts and how they affect the pH and everything like that. So that's the first thing we want to go over today. So I wrote some examples up on the board, and I want to go through with you the thought process that you should be having when you encounter a salt. Once you understand it, it becomes pretty simple. And instead of just memorizing like, oh, the cations of this will lower the pH, or the anions, we want to teach you conceptually so you really understand it. So when you get to the test, instead of just memorizing all these facts and trying to recall that information, you can actually think logically through it and figure it out on your own. Okay? So I just want to jump right into this. Let's start going through these. So the first step that I always do when I encounter a salt is I think, what are the ions? If this was to break into ions, what would be the ions produced? So for NaI, what are my ions? Okay, you're right. I would have sodium ion and iodide ion. Okay? That should be fairly simple to see what ions are going to break up. There's always going to be a cation and an anion. Okay? Step number 2. Does that ion correlate with a strong acid or a strong base? For example, I know this is an anion, so it's going to go with an acid. If I were to stick an H on this, would that be a strong acid or a weak acid? Strong. Exactly. If I were to stick an OH on this, would it be a strong base or a weak base? Strong. Okay, so number 2. Does the ion go with strong, I'm just going to write S, strong acid or strong base? Okay, now here's the first rule. These get really simple because you can immediately start eliminating things from your salt. So we come back here to NaI. Na comes from a strong base. Will this affect my pH? No. No, because conjugates of strong acids and strong bases do not affect pH. So as soon as I see an ion that would correlate with a strong acid or a strong base, I immediately cross this out and say, okay, I know for sure that's not going to affect my pH at all. So let me check the other one now. We already went through this. Iodide is going to go with hydroiodic acid, which is a strong acid. So is this going to affect my pH, this I? No. No. So what we're saying here is if I stick this salt in a solution of water, neither of these ions are going to affect my pH. So my pH stays neutral at 7. Does anyone have any questions on this one? Okay. Let's move on. RbCl. Walk me through it. Step 1. What are the ions?
Rb plus Cl minus.
Rb plus Cl minus. Step 2. Do these ions correlate with strong acids and strong bases? Yes. Rb plus. Yes. Yes. Because if I stuck an OH on Rb plus, it'd be a strong base. So what do I know about this ion? Is it going to affect my pH?
No.
No. Cross it out. Chloride ion.
Strong acid.
Yep. It's the conjugate base of a strong acid. So is it going to affect my pH?
No.
No. Again, if I stick that salt in a solution, we have a neutral solution. And you guys should now be able to start coming back to the thought of strong acids and strong bases produce negligible conjugates. Okay? So if I stick HCl in water, it's going to completely ionize into H plus and Cl minus. And Cl minus is such a bad base, it will never act like a base. It's a negligible base. So if you go back through the slides and look at that big chart that Dr. Macedoni had, you'll see that conjugates of strong acids and bases typically are negligible. And that's why we say here, this is the conjugate acid of a strong base, so it's negligible. This is the conjugate base of a strong acid, so it's negligible. Okay? Is everyone following that thought? Anyone have any questions on this so far? Okay, let's do this next one. What are the ions? Step 1. K plus and
So charge is 2 minus.
2 minus, because I have 2 potassiums there. This would really break up into 2 potassiums, but it doesn't matter for the sake of this problem. Okay, K plus. Does this correlate with a strong base?
Yes.
Yes. So it's not going to do anything. SO3 2 minus. What would be the acid of SO3 2 minus? HSO3 minus. So this is the conjugate base of HSO3 minus. Is that a strong acid?
No.
So is this going to affect my pH?
Yes.
Okay. So this brings us to step 3, which is, will the ion act as an acid or base? Again, this comes back. Strong acids and strong bases produce negligible conjugates. But weak acids and weak bases produce fairly good conjugates that can actually act as acids or bases. So, SO3 2 minus. In a solution, is this going to act as an acid or a base?
Base.
It's going to act as a base, right? It doesn't like this 2 minus charge that it has. It would rather be HSO3 minus. Okay? So is this going to increase or decrease my pH?
Increase.
It's going to increase my pH because this is going to act as a base. This is where it gets hard. If you're still having trouble, think about it like this. You can erase it. SO3 2 minus. Erase this. If you're not sure if it's going to be an acid or a base, just draw it out like this. SO3 2 minus plus H2O is going to make what? This is going to be my acid, right? Because this is, so it's going to be HSO3 minus plus OH minus. Okay? If I'm producing hydroxide ion, when I put this in water, then that means it's a base. So I come here, and I know this ion will act as a base, and therefore it's going to increase my pH. Did everyone follow that?
Yes.
Is it getting clearer? Okay. Okay. Let's do, yeah, I got one more problem. I want to leave these up for you. We're going to post this review, so you guys can do these last 2 on your own. And if you still want more practice, go through Dr. Macedoni's slides because he has a bunch of salts listed, and you can go through them on your own. Does anyone have any questions on these so far? Salts, yeah.
So is HSO4 the conjugate of a strong acid, or is it just SO4 the conjugate of a strong?
HSO4 minus is the conjugate base of a strong acid.
Okay.
Mm-hmm. Yep. Any more questions on these salts? I know it can be really confusing, but I feel like if you break it down into these 3 steps, it gets pretty clear and pretty easy. So again, what are the ions? Does the ion go with a strong base or a strong acid? If it does, it's negligible. And step 3, will the ion act as a base or an acid? If it acts as a base, it increases the pH. If it acts as an acid, it will decrease the pH. So let's do an example problem. Okay, here's a problem. I'm going to give you guys a minute to get started on it. what is the pH of 0.5 molar NH4Cl?
Ammonium chloride.
Remember the steps. We have a salt. Anytime you see a salt, subroutine to the steps.
And we're timing you. 1 minute to get as far as you can. Intentionally solve no mistakes.
What's the first thing you're going to do? Someone shout it out. Yep.
I like that. What are the ions? Right out those steps. Coming up on 5 seconds.
Okay, let's do it. So, NH4Cl, what are the ions? Ammonium ion and chloride ion. Ammonium ion, is it the conjugate acid of a weak or a strong base?
I wasn't very confident.
Not very confident there.
Yeah, I wasn't very confident.
Weak base. Because this NH4 plus would be the conjugate acid of NH3. We know NH3 is not part of our strong base rule, so we know automatically it's a weak base. Okay? So I know this part is definitely going to affect my pH. How about this? Chloride ion. Chloride ion will not, because it's conjugate base of a strong acid. Okay, so now what's the next step? What am I going to do? How am I going to figure this out? Rice table. So first part, write out your equation. NH4 plus H2O is going to be NH3 plus H3O plus. And you guys know just to cross water out by now. So, if you're ever confused about what something is going to do, whether it's going to be an acid or a base, just write an equation out with water, and you should be able to see it pretty clearly. This has an extra hydrogen. It wants to give it away. It's going to produce hydronium and leave its conjugate base of ammonia. So, what's my initial concentration? 0.5. And this is going to be minus X. Then I have 0.5 minus X. My initials for these. 0
Plus X.
plus X plus X,
X.
X, X. What's my next step? Solve for X. Right? I'm going to set up the expression, the K expression. Now, what was I given here? I was given a KB, but I have an acid. Okay? You can never use a KB if you have an expression where you have an acid. So the first thing I need to do is convert my KB to a Ka. And when I do that, I get Ka equals 5.55 times 10 to the negative 10. Okay? So now I'm going to set up my expression. I have 5.55 times 10 to the negative 10 equals product over reactants. X squared over 0.5 minus X. Now, if you're really comfortable using the solver function in your calculators, go ahead. But what I'm going to teach you right now is the assumption rule. Again, if you haven't got it already. This X down here, what you're looking at is your initial concentration and your Ka or Kb value. if there's a difference of a factor of 1,000, so 1 times 10 to the 3, if there's a bigger difference than that, then we can neglect this x. So if I wrote this in scientific notation, it would be 5.0 times 10 to the negative 1. And I know between negative 10 and negative 1, that's a 9 difference. So I know easily I can just neglect this x. Makes my math a lot easier. So now when I continue on, I solve for x, and x equals 1.67 times 10 to the negative 5. Okay? And remember, I'm looking for the pH. How do I solve for pH? Right? This x is my hydronium ion concentration. So I take the negative log of this, and that will give me my answer. And the answer is 4.78. Okay, so let's walk through again slowly the steps. Number 1, you got to figure out if this salt will affect your pH. We figured out it did. Write your equation out, ice table, solve for x, solve for pH. Does anyone have any questions on this? Good? Awesome. Okay. One more problem for me and then Braden gets the top. Okay, one more salt. We love salts. NH4 ClO2 minus. Don't look at the hints I already drew up here. Step number 1. What are the ions? NH4 plus ClO2 minus. NH4 plus, is that the conjugate of a strong base?
No.
No. So will it affect my pH?
Yes.
ClO2 minus, is that the conjugate of a strong acid?
No.
No, because you memorized the strong acids. Will it affect my pH?
Yes.
Okay, so now we have 2 things that are going to affect our pH. This is where you have to compare your Kas and Kbs to figure out which one's going to win out. So in this case, I tell you, the NH4 plus Ka is 5.5 times 10 to the negative 10. And the HClO2 Ka is 1.1 times 10 to the negative 2. What's the first thing I'm going to do? Yeah.
Shouldn't you convert that HClO2 to a Kb?
Exactly. Because I don't have HClO2 in this. I have its conjugate base. So the first thing I need to do is convert that to a Kb. I do that by taking 1 times 10 to the negative 14 divided by the Ka is going to equal my Kb. Right? And when I do that out, I get 9.09 times 10 to the negative 13. So, I have my Ka now and I have my Kb. Now I'm just looking to see which one's bigger. In this case, which one's bigger? NH4 plus. So my Ka is bigger than my Kb, so this salt is going to make my solution more acidic. It's going to lower the pH.
But we don't have to figure out by how much.
No. No. In this case, I just want to ask, what's it going to do to my pH?
Okay.
It's going to make it more acidic. Yeah. Any more questions on this? This salt right here, comparing Kas and Kbs. Yeah, Jim.
But once I figure out which one's greater, if Dr. Macedoni wanted us to continue on with that, to use the K value we came up with between the two, or
Yeah, definitely. He could have you continue on. Once you solve for a Ka, he could have you continue on and actually solve the pH.
so would you use the Ka of the NH4 then your
It gets a little tricky then. Yeah, but in this question, I'm just asking you, how is it going to affect my pH? Just like the salts we were doing. Yeah, Andrew?
Would Ka always be a cation? Or maybe the
Yeah, the Ka is your cation.
will it always be?
Yes.
yes.
Yes. Okay, any more questions on these salts? I hope I get the feeling that this helped, that everyone's kind of getting cleared up on this because it was really confusing. Okay.
So the thing is I know that like when we do this, and some of you are like,
okay, he keeps slamming the steps over and over and over. And I think maybe some of us think, okay, got it. Like, you keep saying that. But the thing is if you're having that feeling, that's a great feeling. If you come to a review and you're like, I know all of this. Like, why did I come? That's actually a very sweet feeling, because that means we're going over stuff that apparently you've mastered. So that means you're pretty prepared to take an exam on this material. So feel good if that's at all how you feel with going over some of the salts. The other thing is you really lower your potential to glitch, like we call it. To glitch on an exam when you write out a stepwise mechanism of solving a problem. Like this 1, 2, 3 way to solve, and you go, every time, no matter what, even if I think I know it, I'm going to ask myself these questions, and I'm going to answer them for real. You will lower your percentage of glitching. Sometimes, what's the worst is when you guys like took your free response exam, get your exam back, and you go, oh my gosh, I knew that, but I didn't write that for some reason. And that is not fun to happen. So please go through the stepwise mechanism of how to solve these. Really internalize that, and you won't miss a solved problem, okay? So if you're chatting, that's totally cool. It doesn't bother me at all, but I think it might bother some other people. I don't care though. So here's the thing. This is what we're going to do. I have a couple problems on the board. Now, I understand that some of this is going to be a little bit like, I've done this a million times in my smart work. I've done this with my recitation leader on the thing, or on the recitation assignment. That's good. What I want you guys to do, will you put that back up? I want you, so that the people can see better. Right there is good, yeah. I want you to start solving these 3 questions, okay? Start solving them. We're going to just take a few minutes, right? I want you to go through, make sure you are understanding these conversions. What I've got on the board are problems where we're converting between POH, pH, H plus concentration, and OH concentration. This is a vital tool into solving problems with acids and bases, especially for this exam, okay? What I don't want you to do, and I know a lot of you are solving as I'm saying this is good. What I don't want you to do is feel embarrassed if you don't know how to do these log rules or something like that, right? If you're like, I don't know, but everyone says that they know, right? You need to be the person that says, I don't know, right? Like when we watch like a Hollywood movie, when they have like those AA meetings or whatever, and someone says, hi, I'm John Doe, I'm a raging alcoholic. Like, there is something good when he does that says, I'm coming out and saying, I have a problem. Like, and that sucks to say, now everyone knows, but there's something psychologically good that happens when you say, I'm a raging alcoholic. Like, I have an issue. So I'm saying, if you are having an issue with this, you need to be like, I have a problem with log rules. And you need to make sure you master this. This is important, okay? 30 more seconds. Now we put it down. Okay, all right, let's start on the first one. I'm going to go over these fairly quick, right? If this is your problem, you need to mark it. And if it's one you think you want to ask now, let's ask it now. If not, please see us after the review, and we'll make sure we smooth over your issues with these things, okay? Number 1, calculate the H plus ion concentration, right? Or my acid, right, that I've got going on, right? Synonymous with what? Hydronium in water. And I have a solution with a pOH of 4.5. What do I do?
14 minus.
I hear a 14 minus my pOH. Why do I do that?
That gives you your pH.
Because it gives me my pH, right? There's the trick, right? A pOH and a pH are related to one another, but they are not the same thing. Both are on a scale of 14, and if I want to get the other one, all I do is take 14 minus what the pOH is, will tell me my pH. So I do that, and then what do I do once I find my pH? I go 10 raised to the negative pH, right? So when I take 14 minus 4.5, I get a pH, right, of 9.5. To get a H plus concentration, I go 10 raised to the negative pH. Really need to hit that home. That's how we do it. You're going to go 10 raised to the negative pH, or 9.5 will tell me my H plus concentration in this specific solution, okay? That's how we do number 1. If that didn't make sense, mark that. Let's talk about it after, okay? Right here. What is the H plus concentration in a 0.25 mole solution of NaOH? What is the OH minus concentration? What do I do?
It's easier to find the OH minus concentration.
Okay. So what is the OH minus concentration? 0.25. And that's because this is a strong base. So if it's a strong base, whatever my solution is originally, I will create that same molarity or concentration of the OH minus, right? So I have 0.25. So 0.25 is this answer. Now there's several things I can do now. What's one of them? If I know my OH minus concentration, what can I do?
You get the POH.
I can get my POH. How do I do that?
Using negative log.
Yep, so if I go the negative log of OH minus concentration, right? That would tell me my POH, and then what do I do?
10 to the negative, that's your number.
Well, if I go 10 to the negative this, I'm going right back to this.
You're right, 14
So then I want 14 minus my POH, right? That's the step we did up here. 14 minus my POH. And then what do I do to get to the end?
And the negative.
Right, so at first I'm going 14 minus my POH, right? That gives me a pH. This is messy, but you guys get the gist here. And then I'm going to go 10 raised to the negative pH gives me my H plus. Okay? There you go. That make sense?
Can you do that?
What? No, I just wrote how to do it. Yeah, just do that out. I think I have the answer. Let's see. So number one, we got, right here. So your H plus, if you did this out, I got 4 times 10 to the negative 14. That's what you should have gotten for your H plus, okay? Let's do the next one. Circle the base and the conjugate acid. This is a simple one. Corbin really drove this home for us. In this equation, if you can see it, where am I going to circle my base? Everybody make a beep noise as I go over it. Okay. What is the name of that? Whoa. I want to hear the dictation at the end of the word. What is this? Ammonia. Ammonia, exactly. Why this is going to be a very important molecule as you go throughout the rest of chemistry. Memorize this one. Ammonia. Okay, it is a weak base. Okay, where's my conjugate acid? What is the name? Ammonium. Memorize these. These are important ones, okay? You will see this a lot. These are the ones you need to get familiar with, okay? Whatever that means. Okay, let's do the next one. You raise that up. So now we're getting into a little bit more of like the meat and cheese of this section, some of the harder problems. So, read, let's see, is this the one I want to do? I think this is. Yeah. Everybody read this really quick. Okay? Formulate in your head for 10 seconds how I would solve this problem, and we're going to go through it. Okay? 5 more seconds. Okay. Somebody tell me what is a few things they notice about the problem. Let's just dissect the problem. Okay? What are a few things about this? Let's talk about it.
You can use the assumption.
You can use the assumption. Immediately he says that. That's great. Yeah, we can use the assumption if we had to do a what? An ice table. Perfect. Yeah, we could use the assumption if we have to do an ice table. I like it. What else? What type of, what am I dealing with here? An acid or a base? Base. How do I know that? Well, I was given a KV, but also because it said ammonia, right? So I memorized that. I know, okay, that's a base. It's a weak base, so I got a KV value. I want to know the OH minus concentration. Are there any shortcuts? Sometimes there's shortcuts with acid base. Are there any? No, I got to go the long route. Okay? So he said ice table. This is valid. Okay, ice table. So let's start off. Rice. When we took Chem 106, they didn't include the R. So I don't know who got involved with making it a rice table. It was an ice table, but I like it. Okay, let's make a good little rice table. Okay, so we have ammonia, and when it acts with water, we're going to get its conjugate acid, which is ammonium and OH minus. Awesome. What was our initial concentration of this? 0.5 molar. Will this lose or gain? It will lose. At equilibrium will be 0.5 minus X. A lot of this is really standard for you guys. Have done really well on this part. What about this? What do I do? Negligible. The whole thing is gone. Why? Because it's a pure liquid. There's a lot of it. Don't need to worry about it. How much do we start at this? 0. We gained x. Coefficient says at equilibrium it equals x. We started with 0. We gained x. At equilibrium tells us, oh, my mind, 0. That we have x here. So let's write an equilibrium expression. I would have x squared, those two, remember, products over reactants, right? 0.5 minus x is equal to KB 1.8 times 10 to the negative 5. Now, the very first thing that someone shouted out was we could use the assumption. Where that comes into play right now. Corbin explained this to us. Our original concentration is different from our KB by a factor greater than 1,000. Meaning, this KB tells me that my reaction is really reactant favored. So that's what makes this a weak base, right? I don't really form a whole lot of this. This is a weak base. It doesn't happen that much. So, and my K value, or my equilibrium constant for a base, like we just went through this whole section, tells me that. So I know that if I start off with 0.5 molar, really, in the end, I probably still have just about 0.5 molar, barely any of it reacted, because that's what this value tells me. Where they're different than a factor of 1,000, I assume that I didn't actually lose any. Does that make sense why we do that? Okay. The rest of this is simple algebra. I will multiply this to this side, and then take the square root of that. You guys should be okay with that. And in the end, did anyone solve it already? In the end, you should get 0.003 molar, okay? That is X, or the answer, right? OH minus concentration. So there are a few things about a problem like this that are important. Hopefully, that was just a breeze for you. I would imagine a problem like this being on your exam, right? Calculating the OH minus concentration, using a KV, but really it's just like equilibrium. We really haven't changed anything. Okay? Let's do the next one if there aren't any questions about this. Feel good about it. Okay. What do we have next? Okay, this brings us to maybe a little bit more difficult of a problem. Okay? Let's take a minute. How about this one's just a little bit more difficult. Read the problem, figure out how to solve it. Okay? Here we go. I'm not very good at this video. Can you guys see? I know I'm really tall and everything, but you know, whatever. Okay, we've got a minute. A minute's gone by. So let's dissect this problem. Figure out what's going on. When I read it, the Ka of hydrofluoric acid. Well, I just know now that it's an acid. So I know it's going to happen in water. If I put it in water, right? I'm going to create an acidic solution, drop my pH. So they tell me that the Ka is this value. Little disclaimer about some of these Kas. If you look in the book and other places, they will vary slightly. This one just came right off a problem that I got from some other source. So don't memorize your Kas, meaning like this is not the perfect Ka for everything. So just so you guys understand that. If you see the Ka of hydrofluoric acid is different, I understand. But for this problem, we'll do it with this. It's really close to this. Okay? For a solution of a concentration that is 0.15 molar of hydrofluoric acid, okay? And I want to know not what the H plus concentration is like we just did with that base, but I want to know what is the percent ionization, right? Something that has thrown a few people off in the tutorial lab that we've noticed. So, how do I solve this problem? What's the first thing that I got to do? With confidence. Boom. Rice table. Okay? We got to do a rice table. So let's set it up. That's exactly what I have to do. So I do my rice. Okay, do this. We're trying to get this thing set up quickly. Hydrofluoric acid, right? It's in H2O. Sometimes I put it up there. It's okay to do that. Okay, we get this. All right. So my initial concentration, I know, is 0.15. Trivial for you guys. Okay, do I lose or gain? I lose. At equilibrium, I'm 0.15 minus x. Over here, I started with 0. Oh, too Right? We started with 0, gained x, and at equilibrium I was x, and at equilibrium I was x. So, Jim.
Since it's a,
Never mind, you got it.
keep going.
I like that, that's good. So we like C. At equilibrium, our expression is x squared products over reactants, okay? Underneath here, our denominator is 0.15 minus x is equal to my Ka here. 7.1 times 10 to the negative 4. So with this one, where are you guys at with the assumption? What do you guys think? Probably not, right? This is one that I'm going to have to do out. Okay, this means the quadratic equation or your solver. Yeah, question?
How would you set that up, like, if you didn't want to just, like, leave off the H2O?
Okay, yeah, let's just redo it with not leaving off the H2O. We'll just change this just slightly. We'll try to leave it so it matches. So, HF, is this what you were wondering?
Yeah, that's what I kind of.
Okay, just to visualize it, what's H2O is going to form H3O, which is synonymous with H+. This hydronium ion is synonymous with H+. And then the conjugate base still.
So, would that be like F minus, I don't know, like, where's the OH?
Oh, there isn't, right? The water didn't lose a H, it gained one. So this just went right to there with this guy with it. And it just left him. Does that make sense? Good. It's a good question because sometimes if you do it one way and see it another, it like throws you off a little bit, and we get that totally. Okay, so this is our equilibrium expression, products over reactant. I can't assume, so I got to do my quadratic. Okay, so this one takes a little bit more time. I'm not going to do the quadratic equation on the board for you. You guys have probably done it a lot. When I do this, I get that x is equal to 0.010319888. Oh no.
Should you change the Ka to Kb? No, I got that.
This is right. I'm just letting you guys just sulk in it for just a minute. Yeah, this is good. So without the assumption, okay, but is this the answer to my problem? No. So maybe when this was done, they assumed, but you're right. This is without. It's a valid. You shouldn't assume. In the end, I'm going to show you how they're going to change, so you're valid. Okay, so this is what I would get, x, right? If you did the quadratic, it's going to be something a little bit different. But this isn't the answer to my question. The question is, what is the percent ionization? So how do I solve for that? Okay, here's the equation for percent ionization. Here it is. I'm just going to write this right here. Equation is that my H plus concentration over my original acid times 100 is equal to percent ionization. Okay? So, H plus concentration equilibrium over the original acid, how much originally or initially, right, times 100 gives you my percent ionization. So, this is what's confusing for some people. Let me explain briefly, just really quickly, what that means. Okay, percent ionization is important because it'll answer a lot of our questions. Okay, so a lot of times what confuses people is why do I use my original on the bottom and not like at equilibrium? Because what percent ionization tells me is kind of exactly like the label is. The percent that something that isn't an ion originally, it's just a compound, is breaking up to form ions, right? If it's something that is weak, if it's a weak dissociation, like a weak acid or a weak base, that means that when I drop that in water, not all of those molecules will separate into ions. Some of them, when that happens, they'll separate, but like the fluorine here will reach back and still an H back. And so in the solution, you will have some that remained as hydrofluoric acid and some that ionized. I want to know the percent that happened. So I got to take my original that I started with. What did I put in the solution? And compare that to how much ionized, right? So the equation is how much ionized, or my H plus concentration divided by my original amount, times 100 to make it a percent, right? So there are all kinds of questions that can be asked using percent ionization. Okay, question?
And so percent ionization for bases, you would just do OH
Mhm.
over the original concentration of the base.
Yeah.
Okay.
Exactly.
Cool.
Okay. Does that make sense? So let me ask you guys a conceptual question that comes to mind before I write the answer up here on the board, and we'll realize that what she said over there was a really, really good point. Can someone explain to me why is it that when I look at HCl, HBr, and HI, those are strong acids, but when I look at HF, which is in the same, the conjugate base is in the same column, why that one is not a strong acid? Who could answer that question? Like, in realistically, what is happening in the front? First hand up.
I think it's because the HF bond is stronger than the H2O bond, and
Okay.
so it will